Hey everyone, here we are again for another Edexcel Combined Science Chemistry paper. In this case, it's June 2018. Okay, so it's paper 2 of 2018. So, question 1 says, the Earth's atmosphere contains several gases. Figure 1 shows the relative amounts of gases thought to be in the Earth's early atmosphere. Figure 1's right there. The amount of water vapour in today's atmosphere is much less than the amount in the Earth's early atmosphere. Explain why the amount of water vapour in the atmosphere has changed. Well, water vapour means gas, water gas. Yeah, water is a gas. So, why would it have gone down over time? Well, remember, as the Earth's atmosphere was formed by those volcanoes, it was very hot. So essentially, okay, the Earth cooled down, okay? Let's write that again. Earth cooled down. Okay, if the Earth cooled down, what's going to happen to the gas water? Water vapour. It condensed. It did. It condensed. Fell as rain. I'm going to write more than you need to, because why not? Fell as rain and formed oceans. Again, another paper may ask for something more specific than that, so I thought I'll write it all anyway. So, it condensed, fell as rain, and formed oceans. Job done. Right, B says the apparatus shown in figure 2 is used to find the percentage of oxygen. There it is. Calculate the percentage of oxygen in this dry air. Now, initial volume of air is 50, final volume of gas is 40, so 10 of it's been used up, basically. 10 centimetres cubed of it has been used up. Okay. So you've got, first thing you got to do is work that out. 50 minus 40 equals 10 centimetres cubed used up. Okay, and what you then do is take that 10 and divide it by 50 and then times that all by 100, okay, to get your final answer of 20%. Okay. At the end of the experiment, the apparatus and its contents were allowed to cool before the final volume of gas was measured. It must be allowed to cool because reading the volume while the apparatus is hot is dangerous. The glass tube may crack when it's hot. The gas is expanded and the copper reacts with other gas in the air when it's hot. Now, the reason is, of course, the gas has expanded. If you're measuring volumes, you need to make sure you're measuring at the same temperature to preserve the same volume. Earth's earliest rocks contained iron sulfide and no iron oxide. Later, the rocks contained iron oxide as well as iron sulfide. Explain what happened to allow this change to occur. Well, sulfides are formed when there's no oxygen in the atmosphere. Then obviously oxides require oxygen. Okay, so oxygen must have increased. Oxygen in atmosphere increased. Okay, and that reacted with the iron. Reacted with the iron or iron sulfide. There we go. Nice, what's next? Oh, a blank page, then the end of the row. Wow, we are flying through this. Anyway, I think I've said that in every single video. Right, a chlorine atom contains 17 electrons, 18 neutrons and 17 protons. State the mass number. Well, you know the mass number is the total number of neutrons and protons, so hopefully you can add up 18 and 17 to make 35. If you can't, use your calculator. Right, what is the electronic configuration of this chlorine atom? So we've got 17 electrons, let's work through this. We've got 2 in the first shell, leaving us with 15. We've got 8 in the second shell, leaving us with 7, and then 7 in the final shell. That is the electronic configuration. Please note they don't want the big old diagram. If they did, they would have given you more space. Describe what you would see. I love the fact they emphasize see. What would you see if damp blue litmus paper was placed in chlorine gas? Right, well, the test for chlorine gas is damp blue litmus paper. Okay, it turns red, then white. White. That's what happens. Damp blue litmus paper turns red, then white. In chlorine exists as diatomic molecules. In a molecule, 2 chlorine atoms are joined by a covalent bond. Describe what is meant by a covalent bond. Well, very simply, the definition is it is a shared pair of electrons. Now, why is that 2? Well, it's 1 for shared electrons and 1 for pair. Okay. Explain why chlorine is a gas rather than a liquid at room temperature. Well, essentially, it has weak, being a simple covalent, it has weak intermolecular forces. It has weak intermolecular forces, which require little energy to break. Energy to break. That's why. Nice. Now, hang on. I can't see this next question because there's a little toolbar in the way. No, I want a pen. Okay, let me move this around. Yeah, the little toolbar is in the way, means I can't see it. Right. Can I just... Yeah. Okay. When a gas hydrogen chloride is dissolved in water, a solution formed. Blue litmus paper dipped in this solution turned red. Explain why the paper turned red. Okay. It's because it contains hydrogen ions. Hydrogen ions, because that makes it acidic. Fantastic. Okay, what's next? Lithium, sodium, and potassium are reactive metals in group 1 of the periodic table. It tarnishes an air to form a layer of sodium oxide. 0.92 grams of sodium oxide combines with 0.32 grams of oxygen in this oxide. Calculate the empirical formula of sodium oxide. Now, you remember, hopefully, fingers crossed, the empirical formula is the simplest whole number ratio. So, what do we do here? Well, you take 0.92 and 0.32. Okay, that's the sodium. So you divide them by the MR, which is or the AR in this case, which is 23 and 16. That gives you 0.0. Just having my calculator 4, and that one is 0.02. Now, to find the simplest whole number ratio there, you very simply divide them both by the smaller value to give you a ratio of 2 to 1. Therefore, it is Na2O. Job done. Now, it says sodium reacts with water to form sodium hydroxide solution hydrogen. Complete the balance in the equation and add the state symbols. Now, you will be expected to know state symbols of various things, okay? The only slightly iffy one here is sodium hydroxide, but it tells you that's a solution. That means that one is indeed aqueous. Hydrogen, you should know, is a gas. Water, you should know, is a liquid. And sodium, you should know, it's right in the right place, is a solid. Okay. Now, how are we going to balance this bad boy? Let's work this out. So, we've got, let's have a look, 2 H2Os, which means 2 oxygens. To get 2 oxygens on this side, we need 2 NaOHs. Okay. So, we've now got 2 oxygens. Great. We've now got 2 hydrogens here and 2 there, so that's 2 plus 2 is 4. Now in 2H2O there's also 4. Brilliant. Now we've got 2 sodiums here, only 1 over here, so we need a 2. Job done. 3 marks. 1 mark for the state symbols. So what I'd say is, even if you're sitting there thinking I cannot balance equations, bang some numbers in there, because you might as well have a go. Just stick 2 in all the boxes. If you're really not sure, have a guess. But you should be able to do the state symbols, okay? And you'll get 1 out of 3 just for doing those, which is a reasonable amount of marks. In an experiment, equal-sized pieces of lithium, sodium, potassium are added to separate samples of water. A flame is produced only with potassium because potassium, well, we know, is the softest metal. Does that mean the flame is produced? Has the lowest melting point. Again, does that result in the flame? Is the most reactive. That's why. Is the only flammable metal. Well, I mean, is the metal burning? Or is it the gas that's generating which is burning? The other 3 are totally irrelevant. Explain in terms of electron configuration, the increase in reactivity from lithium to sodium to potassium. Okay, so as you go from lithium, which is 2.1, to potassium, which is 2.8.8.1, okay, outer shell electron gets further away. Outer shell electron further away. Okay, that means it's more easily lost. Remember, you're trying to lose one. It's more easily lost. Okay, group 7, of course, would be the opposite, but this is asking you about group 1. Right, page 4. Here we are. Page 4? Question 4. Here we go. Now, there we go. Gives a fraction column and some parts of the fractions that are given off. The properties of these fractions vary from the top of the column to the bottom. Which of the following is a trend in properties obtained from the top to those at the bottom? Okay, so it's the trend as you go. It's the trend as you go down. Okay. Now, as you go down, the average number of carbon atoms decreases. No, it doesn't. It increases. It's not A. The ease of ignition increases. No, it doesn't. It decreases. The boiling points decrease. No, they don't. The boiling points increase. The viscosities increase. They do indeed. Okay, remember viscosity, essentially I like to refer to it as runniness, but it's the opposite of runniness. So something that is very viscous is not very runny. What is the general formula of an alkane? Well, hopefully you've just learned that it's D. If you haven't just learned that it's D, go away and learn that now. There's no real way to figure that out. Well, there is, but you'll spend ages trying to do it, and it's probably easier just to learn it. I don't like telling you to just learn stuff, but that's one of those things. It's easier to just learn. Right, what's next? Oh, a graph. Oh, 2 graphs. Right. Why are alkanes described as hydrocarbons? Okay. Now, the key here is a hydrocarbon contains only. That's the key. Only. Okay. Contains hydrogen and carbon. And carbon. Now, if you want to be really fancy and write a really good definition, you would say they are compounds that only contain hydrogen and carbon. That's a really good definition. Now, compounds that only contain hydrogen and carbon. Okay, figure 4 shows the graph of the boiling points of some alkanes against the number of carbon atoms in one molecule of each alkane. There you go. So, explain the pattern shown on the graph. So the first thing you need to do is state the pattern shown on the graph and then say why. Okay, so as you can tell, as the number of carbon atoms increases, the boiling point increases. Carbon atoms increase. Hang on, increase. My little finger's getting in the way today. The boiling point increases. So that's the pattern. That's the trend. That's one mark. But why? Okay, it's because there are stronger intermolecular forces, essentially, which require more energy to break. Stronger intermolecular forces. That's the reason. There are stronger intermolecular forces. When crude oil is separated into fractions, the amount of each fraction is obtained rarely matches the demand for that fraction. Figure 5 shows the relative amounts of 6 of the fractions present in crude oil and the relative demand for each of these fractions. There's a graph on there. Use the information in figure 5 to give the name of the fraction that is most likely to need to be cracked. Now, of course, cracking is breaking them up into shorter pieces which are more useful. So which one of those basically has the most but the lowest demand is what we're looking for there. Okay, as you can see from this, fuel oil has nearly 50% but a much lower demand. Therefore, that one would be, where's my pen gone? Fuel oil. Okay, that's what that one would be. The little cursor that uses my pen is now gone. Fuel oil. Okay, in a cracking reaction, reactants are heated to form products. This reaction is endothermic. On the axes provided, draw a reaction profile diagram, label the energy of the reactants, the energy of the products, and the activation energy. Oh, this is going to be painful with this pen. Anyway, I'll do my best. however, I will need you to be far better. There was a little cursor on the screen telling me where the pen was. It seems to have there it is, it's come back. So, essentially, we've got our reactants. I'm just going to write rea because I can't fit it in there, but write reactants when you write that, okay? And they're down here in a nice straight line, as straight as you can, please. Now, they then go up and down a bit, and of course, like that's too straight, don't do that. And you've got to remember that these are the products. Okay, these are the products. So you've drawn your nice curve, and you've now got to label your activation energy. Now, make sure what I would do if I was you, when you come to do this, you've got a line from here all the way up to the very peak of your curve. Okay, the very peak of your curve. I would even go so far as to maybe draw a dashed line from there to show that you've done it. Use a ruler just to show that you've done it to the right place. It shows understanding, which is important, okay? And then don't forget to label it as activation energy. Don't forget to label it as activation energy, okay? So there we go. A lot easier to do by hand, I'll be honest with you. Right. Dodecane can be cracked to form useful products. Complete the equation of the cracking of dodecane by filling in the formula. Well, all you've got to do is figure out how many C's are left over once you've taken these into account. And if you have 12 on this side, 3 times 2 is 6, meaning there are 6 left, aren't there? There are 6 left. And we have 26 on this side. 3 times 4 is 12. Therefore, there must be 14 left. So it's C6, H14. Job done. Nice. Now, it says, describe what is seen when chlorine water is added to potassium bromide solution and the mixture shaken. Okay. So, what will happen to it? Now, all you've got to say there, okay, is that chlorine water has a fairly light colour, okay, but then when you've mixed it, obviously you'll then see the bromine, okay. So initially, it's fairly colourless. It's fairly colourless, but afterwards it's reddy brown, red/brown, which is the bromine colour. Okay, in this reaction chlorine has been reduced. Here it is. You explain using the equation how you know that chlorine has been reduced. So remember, chlorine atom forms chlorine ions, and when Cl2 goes to 2Cl minus, it gains an electron, okay? So the chlorine gains an electron, okay, and that forms chloride ions. Now be careful with calling this chlorine and those are chloride. Okay, again, be careful with your language here. Do not call it a chlorine ion. Okay, write the half equation for the formation of bromine from bromide ions. Okay, well that's the opposite of this essentially. So you end up over there with 2Br minus, okay, which gives you Br2. But we are missing something from here. What are we missing? Hopefully you're screaming at me. What about the electrons? And they actually go on this side, okay? There's 2 of them because they're given out. So each Br minus gives out an electron. There are 2 Br minuses, so 2 electrons are given out. Aluminium reacts with chlorine to form aluminium chloride. Write the balanced equation for this reaction. Now, you then need to write, so we've got Al plus Cl2 makes aluminium chloride. Now, this seemingly assumes that you know the formula of aluminium chloride. Now, hopefully you know that aluminium, being group 3, forms a 3+ ion, therefore there must be 3 chlorines. to balance out the 3 plus ion, okay? Because you've got an Al 3 plus and then 3 Cl minuses to balance this out. Now, knowing that, we've now got to sort out these number of chlorines. We've got 2 and 3. The easiest thing to do is make them both 6 by having 2 of those, 3 of those. We've now got 6 chlorines and 6 chlorines. Now we've got 2 aluminiums. It's just bang a 2 in front of there. Job done. And what I've now done is scribbled all over the next question. A solid ionic compound is dissolved in water to form a solution. Describe a simple experiment to show that charged particles are present in this solution. So what you would do is you would get your solution. Yep, you would stick a cell with a bulb, okay, a bulb and a battery in it. You would stick that in there with an electrode, obviously complete the circuit with another electrode. Now obviously then if there are charged ions in there, charged particles are present in the solution, that bulb would light up because the electrons would be transferred to the solution. So insert electrodes, into solution, connect to cell / bulb. I mean, you could use a voltmeter, you could use an ammeter, it doesn't really matter. Connect to cell / bulb, and bulb lights. And that will show you there are ions, charged particles. Okay, oh look, that is the end. There's the big long question, but we'll tackle the rest of it first. Question 6 says, the rate of reaction between magnesium ribbon and dilute hydrochloric acid at room temperature is investigated. The apparatus used is shown in figure 6. Graph 7 shows the experiment's results. State a change that could be made to the apparatus in figure 6 to measure the volumes of gas more accurately. Now, you may not remember doing the experiment that way. You may remember doing the experiment that way. I never do it that way, okay, because I always use, where's my pen? I always use a gas syringe instead, which is much easier to use and gives you a much more accurate volume of gas. Okay, it says a tangent has been drawn on the line in figure 7. Calculate the rate of reaction at this point. So all you've got to do then is make your little triangle. And remembering is the change in y. Okay, so change in y over the change in x gives you your tangent. Okay, so pick nice simple values. You could use the change in x and make it 60. That's a nice easy value to work out. You've got a calculator. If you haven't got a calculator, try and make it 10 or something, or 20, something easy to divide by. Okay, but you've got a calculator, so it's 60. And you just got to work out the change from there. Now, the highest point there is 43, and the lowest point to me looks like 15. So it's 43 minus 15 up here. Okay, so 43 minus 15 up here. Okay, and then tap that into your calculator as I'm doing now, and it gives you a rate of 0.47. Good stuff. On the graph in figure 7, draw the line you would. Please make sure you do these questions, okay, because this one might be missed. On the graph in figure 7, draw the line you expect to obtain if the magnesium ribbon was replaced by an equal amount of powder. Now, if it's powder, it's going to be faster, and what that means is your line will be. Now, I can't draw very well on this tablet, but your line will be steeper. Please note, however, it will finish at the same point, okay? Now, I've drawn that terribly, okay? This line should be at 40. It should finish at the same point as the other one, okay? So, key point here is you've got a steeper curve, okay, and finishing at 40, steeper. It's very hard to draw with this tablet thing I've got going on. Steeper curve, finishes at 40. Practice drawing those, because this is a common question. Here's a balanced equation. In another experiment, 0.1 moles of hydrochloric acid were reacted with 0.1 grams of magnesium ribbon. Calculate the number of moles of magnesium in the 0.1 gram sample of magnesium ribbon. Okay, now you know, hopefully, the moles is mass divided by MR. Okay, so all you've got to do there is do 0.1 divided by 24, which gives you, tapping into the calculator, 4.2 times 10 to the minus 3, okay? Or if you're just one of those fancy people who just likes decimals, 0.0042. Either is acceptable, okay? Either is acceptable. Now, next, in a further experiment, 0.5 moles of hydrochloric acid was mixed with 0.5 moles of magnesium. Okay, use the equation to show that in this equation, magnesium is in excess. Okay, now all you've got to say there is that looking at our equation, 2 moles of HCl react with 1 mole of Mg. Okay, so 2 moles of HCl react with 1 mole of Mg. Okay, meaning you've got way too much magnesium there. Finally, the last one, the coup de grace, the 6-mark question. Now, as I said, I've said this in previous videos, I'll say it again. I like these in Edexcel because you get 2 questions in one. You get to talk about 2 things at once. So, let's see what's going on here. So, we've got concentration of A being 10, and then 10, and then 40, and then the temperature being 20, then 40, then 40, and the time for cross to become invisible. So, you need to talk about, first of all, let's talk about concentration. So, you need to find the 2 experiments where the concentration changes. So, you're going to use either 1 and 3 or 2 and 3, okay? But, hang on, if you're going to change the concentration, do you need to keep the temperature constant? Yes, you do. Therefore, you're going to use experiment 2 and experiment 3, because you need to keep the temperature constant, or it's not a fair test. Now, basically, when the, what that says, as the conc was higher in experiment 3, okay, time decreased. There we go. 1 mark, just for saying that. All you're reading off there. So as the concentration goes up by 4, the time for the cross decreases significantly. Okay, now why is that? That's because, remember, there are more particles. Okay, now if there are more particles, what does that mean? That means a greater frequency of collisions. Remember, don't just say collisions. You've got to say frequency or something to indicate that it's collisions per unit of time rather than just collisions. There's a greater frequency of collisions. That means a higher rate of reaction. Okay. Now, next, we've now got to talk about temperature, which I'll do over here. Okay, so there we've got to find one with, it's 1 and 2, isn't it? Because therefore the concentration doesn't change in 1 and 2. Okay, so here the temperature doubles, but the concentration remains the same. Nice. So as you increase temperature, okay, the time taken also decreases. There's a couple more things to say when you talk about temperature. Okay, so you're going to say that as you increase temperature, particles have more energy, which they do, and therefore move faster. Okay, now this will lead to more collisions, but there's another thing you can say if you really want to be fancy and show off. You can say that now more particles now have the activation energy. Okay, just to really bombard them with your understanding, you can say that more particles now have the activation energy. What this means is both of these things result in a greater frequency of collisions and therefore a higher rate of reaction. There we go. So basically it's 3 marks for each experiment-ish, okay? But make sure you talk about both of them, okay? Because there's one experiment there and there's a second experiment there, okay? Meaning you get more marks for talking about 2 things. Brilliant, guys. There's the end of another exam walkthrough. I hope it was useful, and I will see you soon, hopefully, for another one.